Students, friends of BSc second sem, I'm here to discuss with you or highlight with you the last topic, statistical physics. And see, this topic is of 5 hours and the number of questions, multiple choice questions will be asked on this. 3 questions, that means for 6 marks. When it is for 6 marks and it is for multiple choice questions, see this statics basically will go for a word statics here. Statics is a branch of science which deals with collection of information, classification of information, tabulation of numerical data, and the explanation. For example, we are passing through a stage, a situation known as COVID pandemic. When it comes to how many people, how many lives have affected, how many have, so they will make a list. There are warriors who people work on them and they get the statistics, the data, and then how many have infected, how many have come out of that means, and how many have succumbed to it. That is the statistics. Right now they are using it. Well, even in a game like the Olympic is approaching, any game you can say, they provide the statistics of previous games, who has scored highest, who has recorded many things. So that is statistics, and this statistics based on the principle called as probability. Well, we are not studying statistics, but when this statistics is applied to subject like physics, where they will apply this statistics, when they apply to the physics, a new branch emerges and is known as statistical physics. Earlier, people used to study this as statistical mechanics. In statistical mechanics, for example, a thermodynamics, we know, we have studied that is second and first law of thermodynamics. In fact, laws, they do not give the accurate picture here. That is the macroscopic properties of a system, say temperature, pressure, volume, and this temperature, pressure, volume of a system is the macroscopic parameters. When we study microscopic state, that is taking atoms, molecules, and then when we find a macroscopic parameter like pressure, temperature, it gives the average value of that system, or what is known as most probable properties of a system. And this most probable properties of a system, for a thermodynamic system, you can say it determines the average or most probable value or most probable property of a system. That may be a parameter called as temperature, parameter called as pressure. Temperature, pressure and volume are the macroscopic properties considering the microscopic state of atoms or molecules. So here people, they study for thermodynamics, for a mechanical properties. Later on, person like Maxwell, Gibbs, they have applied this statistical physics to a system where a lot of degrees of freedom are there and a lot of infinite number of particles are there. It is impossible to study the property of individual molecule or atom. It is impossible. When such situation arises, when there are infinite number of degrees of freedom for the system, and when there are infinite number of molecules or atoms, when you talk about Avogadro number, n, it is 6 into approximately 10 raised to 26 gram per mole, right? That is such a huge number. So we cannot apply or we cannot measure any parameter of individual molecule, but here using the principle of statistics, that is probability, equal probability and so on, we are getting the property called as most probable property. We are not going in detail about this. So based on this, what is called as a statistical physics deals with macroscopic system, that is a system consisting large number of say particles like atoms, molecules, etc. It is not concerned with the individual or behavior of individual molecule or the atom, but it takes into consideration average or most probable property of the system. The study of statistical physics mainly classified into say two categories. One, I'll write here, that is classical statistics, classical statistics, and the other one is quantum statistics. Second, you can say quantum statistics. So this classical statistics employs classical result of Maxwell's law of distribution of molecular velocities, and already we have done this, that is Maxwell's law of distribution of velocities, and say a Boltzmann theorem relating to entropy. You have come across this in thermodynamics, entropy. Okay, say probability. Now here what we call it is as a Maxwell's Boltzmann statistics, because he has applied to classical physics, and therefore it is called as classical statistics. And he explained successfully using this classical statistics what it is, what it contains. We'll answer these questions. In classical statistics, using say, or you can say in a classical statistics, Maxwell and Boltzmann, they have applied these statistics to temperature, pressure, energy of a system. But this classical statistics fail to explain the observed fact like Planck's law of radiation, specific heat at low temperature, because it has failed somewhere, like while knowing the Planck's law of radiation, or to find or to determine specific heat at low temperature, or either it is a gas or a particular system, people have a new approach to this. Bose, Indian scientist, and Einstein, Fermi, and Dirac. Together, Bose and Einstein, they applied this statistics which has been improved over the classical statistics, and they applied this for a discrete exchange of energy between the system. Both these statistics, known as BoseEinstein Statistics and Fermi-Dirac Statistics, they together is called as quantum statistics, because they apply this Planck quantum concept of discrete exchange of energy between the systems. So this later on it is called as Bose-Einstein Statistics, a quantum statistics, and then Fermi-Dirac Statistics. Fermi-Dirac Statistics. What we want to know under this topic called as statistical physics is, say, Maxwell-Boltzmann Statistics, MD, or Maxwell's Boltzmann Statistics. It is also known as MB Statistics. This is classical statistics, and to say about this classical statistics or MB statistics, this MB statistics or Maxwell-Boltzmann statistics you can say, is applicable to the identical particles. Particles are here assumed to be identical, and these particles are distinguishable. That means you can distinguish me from the others, right? So like that, particles are identical here, particles are distinguishable here, and these particles, they do not have any spin. They do not have any spin. So point to be remembered, particles are identical, distinguishable, particles are distinguishable, and these particles, say, do not have any spin. The examples of such a class of particles, say, molecules of the gas. Example, molecules of the gas. We are preparing for 3 questions as per the blueprint here. That means 3 questions, 3 into 2, that is 6 marks on this. So no, I don't think it is required here to go for a detailed derivation. For this, the other class of this is Bose-Einstein Statistics. Bose-Einstein Statistics, BE Statistics. B stands for Bose, E stands for Einstein, Statistics. In Bose-Einstein statistics, particles are also considered as identical. Particles here identical. Fine. Particles are, say, indistinguishable. They cannot be distinguished. Particles are identical, indistinguishable. Say here, particles are indistinguishable. These particles, either they will have zero spin, or they will have integral spin. Spin of a particle. These particles are normally called as bosons. Particles which obeys the statistics known as Bose-Einstein statistics, they are called as bosons. Fine. And the examples of these particles are, say, helium atom at low temperature. At low temperature is one example. Photons are also called as bosons. Helium atom. Here are certain examples of Bose-Einstein statistics. What comes to this Fermi Dirac statistics? I'll write it here. Fermi Dirac statistics. See, in Bose-Einstein statistics here, this bosons or Bose-Einstein statistic doesn't obey Pauli's exclusion principle. Pauli's exclusion principle. Fine. A. Fermi Dirac statistics. Fermi Dirac statistics. Fermi Dirac statistics are known as FD statistics. Particles here, a class of particle are identical particles. They are also indistinguishable. Particles are indistinguishable. You cannot distinguish the particles here. These particles obey, means Fermi Dirac statistics particles obey Pauli's exclusion principle. You have to remember this principle. Obey Pauli's exclusion principle, which is used in quantum mechanics. These particles known as FD statistics, particles which obeys the FD statistics, Fermi Dirac statistics, they are known as fermions. Fine. And these examples of fermions here, say electrons, say protons, neutrons are the examples of fermions, or they are called as fermions here. These particles are known as fermions because they obey this Fermi-Dirac statistics. Fermi-Dirac statistics. Well, I'll come to this point now. What is called as Maxwell distribution, right? So to say something about this Maxwell's Boltzmann statistics, known as MB statistics. Now, how these particles are, say, distributed. What is the distribution function? That means we have called as phase space. Phase space is something, it is 6-dimensional space. 6-dimensional space where we have 6 coordinates x, y, z for position coordinate, and we have px, that is momentum coordinate, py, pz along 3 direction, altogether 6-dimensional space. A particle, its momentum and its position can be located using these coordinates, and that coordinate space is known as phase space coordinates. Phase space you can say, it is called as phase space. Once we have this position coordinate, we have called as, for a dynamical system, it is momentum coordinate. Together we have this phase space coordinates, and this phase space coordinate, simply it is denoted by, say, thus, that is dx, dy, dz, and say dpx, dpy, dpz. Right, 3 are for momentum and 3 are for the position. Together it is called as phase space. Now, when it comes to the distribution of particles in phase space, so in this classical statistics known as Maxwell-Boltzmann Statistics, this phase space is divided into compartments or energy intervals or groups, like this, compartments, and each compartment is further divided into cells. Say this is one cell, this is another cell, it is like the cells are divided. Now, if there are Ni particles, okay, Ni are the particles, and say here Gi are the cells or the compartment here. Phase space is divided into number of cells. Now, here in Maxwell-Boltzmann statistics, there is no restriction on the size of the cell. There is no restriction on the size of the cell. Okay, so, and there is no restriction on how many particles can occupy a cell. No restriction at all. In what way this Ni number of particles can be distributed in GI cells? And this distribution function here for this classical statistics called as Maxwell-Boltzmann Statistics is given by this, that is using permutation and combination. Say this is omega is a distribution function, you can say it is, say, Gr raised to Nr. Here, the number of ways it is distributed. omega, further it is written as Ni, that is factorial Ni into Zi, or the number of cells, Ni are the number of particles, divided by Ni factorial. This is distribution function for the particles. Means if there are 3 particles, those 3 number of particles, in how many ways we can distribute them in, say, so many cells or compartments, because we are having a constraint here. The number of particles are constant and the energy of the system is constant. Ni is constant. So we are going for an equilibrium condition, and for energy of the system is constant. So further we are going to have what is called as energy distribution function based on this classical statistics. And the energy distribution function known as Maxwell's Boltzmann distribution law of energy for Ni particles. Ni particles, this will be equal to Gi e raised to alpha plus beta times Er. So this beta is alpha and beta are the constants. So if beta is equal to 1 over K, the Boltzmann constant, T is the absolute temperature, then this Ni is equal to Gi, the number of cells here. Ni are the number of particles, e to the power alpha plus, say, Ei upon Kt. You should remember this formula. You should remember this, that is omega distribution formula. We'll solve some examples based on this. To arrive at this, they apply the laws of kinetic theory of gases and some conditions under which this Maxwell-Boltzmann statistics is developed. Condition is that, say, no restriction on the, say, size of the cell. What is the size of a cell here? There is no restriction. How many particles can occupy in a given cell? That is a smallest size. There is no restriction. So what are the types of particle? Particles are identical and particles are distinguishable. They are not like particles, unlike particles. That means one particle can be named with its name. So we have in a class 120 students. Each will be given a roll number and roll number against his name. One person is different from the other. They are distinguishable. So here they are not like particles, but they are identical particles. So looking at the situation, we have come across the 2 formulas here. That is energy distribution formula and the number of particle distribution formula. So because we want them to solve some numerical examples here for objective type. This is about what is called as Maxwell-Boltzmann statistics. Similarly, we'll go for Fermi or, say, BoseEinstein statistics. In BoseEinstein statistics, the class of particle, they are identical. BoseEinstein BE statistics. In this BE statistics, particles are identical, no doubt. We are studying statistical physics for identical particles, right? Particles are identical, no doubt, but particles here are indistinguishable. We cannot distinguish one particle with the other. If we have say for example so many photons, we cannot differentiate them, we cannot recognize them, we cannot write them with a letter or name here. So particles are identical and indistinguishable. These particles, they have the spin of this particle, either it is 0 or integral multiple. They have the spin integral multiple. These particles are known as bosons. These particles are known as bosons. Now, in quantum, this is known as quantum statistics. When we have phase space, as I have mentioned in short, that phase space is divided into compartments, and further one compartment is divided into a cell, and the size of the cell here, the size of the cell is in the order of Planck's constant Q, size of the cell. Planck constant Q. We know the value of Planck constant, which is universal constant, that is 6.625 into 10 raised to minus 34 joules into second. So size minus 34, size of the cell, size of the cell. No doubt this Fermi Dirac, it is BoseEinstein Statistics doesn't obey Pauli's exclusion principle. I said here Pauli's exclusion principle, that is one particle in one state. One particle, in simple way, one particle is arranged in one state, that is energy state or energy level. It is not applicable here. It is not applicable. So what is the distribution function? The number of particles, how many ways they are distributed. In BoseEinstein Statistics, we need this formula. Say this will be equal to, say, Ni are the number of particles, Gi are the number of cells, factorial divided by Ni factorial into Gi factorial. Gi factorial. This is the number of particles, how they distributed, number of particles distributed in Gi cell. If Ni is equal to 4, say Ni is 3 and say Gi are 4, you can calculate this Ni plus Gi, Ni factorial plus Gi, Ni plus Gi, then factorial divided by this, you will get the number of, the distribution. It is based on Stirling's formula, which we are not going in detail.